Welcome back to chemistry class. Today we are going to talk about chemical properties of alcohols. Introduction. The molecule of an alcohol consists of an alkyl group and the functional group OH. The carbon-oxygen and oxygen-hydrogen bonds are both polarized, with oxygen atom carrying a partial negative charge, and yet it has an unshared pair of electrons. This is the reason why alcohols are highly reactive, because on oxygen we have unshared electrons to donate, and again the bond between oxygen and hydrogen, oxygen and carbon are highly polarized, and then oxygen can attract electrophilic reagents. The reaction of an alcohol therefore consists of three main parts. We have cleavage of OH bond resulting in electrophilic substitution of hydrogen, then the cleavage of carbon-oxygen resulting in the either nucleophilic substitution or elimination, and finally oxidation of carbon atom carrying OH group for primary and secondary alcohol to give carbonyl derivatives. This is to mean tertiary alcohols never undergoes oxidation. Let us start with part 1. This part consists of the reactions involving the cleavage of OH bond. Let's see them. The very first reaction is the action of electropositive metals on alcohols. Electropositive metals like sodium, potassium, etc. react with alcohols forming alkoxide or metal alcohols with the evolution of hydrogen gas that produces pop sound or pop motion. Here we have a general equation where ROH, an alcohol, is going to react with the M, a metal, and the metal replaces hydrogen to produce an alkoxide molecule. Here is an alkoxide of metal, and the hydrogen gas is produced. This is a similar reaction as the one observed for water, but water is much more reactive than alcohol. Let us have an example. Ethanol reacting with the sodium metal. This gives sodium ethoxide and hydrogen gas. Second reaction is the reaction with strong bases. Alcohols behave as weak acids and they react with strong bases to produce alkoxides. Here we have an alcohol which is going to react with MOH. This M represents any metal, any reactive metal, and the total molecule is representing an alkaline molecule. When they react, it will be a neutralization reaction, where an alcohol is behaving as an acid and the base plays a role of base, which will produce a salt and water. And this is a neutralization reaction. Here we have an example. If ethanol is reacting with sodium hydroxide, this will give sodium ethoxide and water as a neutralization reaction. Note: alcohols are amphoteric because they behave as weak acids when they react with strong bases, and also behave as weak bases by reacting with strong acids. Here we have an example. An alcohol reacts with the hydrochloric acid to give an oxonium ion and the chloride ion. And this is a salt, this is an acid, and this alcohol will behave as a base. Previously, we saw that alcohol was reacting as an acid because it was together with a strong base, which means that any substance which reacts as acid when it is together with the base and reacts as a base when it is together with acid, we call that substance amphoteric. But they are neither acidic nor basic enough to affect litmus paper. That's the reason why, more generally, they are described as neutral, which means that if you use acid-base indicator in an alcohol, it will not show you any change because it is not strong enough to change the color of indicator. The third reaction is alkylation reaction and etherification reaction. Alcohols react with the alkyl sulfate by replacement of the hydrogen of the functional group by an alkyl group, forming ether or alkyl derivative, or the same or different two alcohols react to give ether. The alkyl sulfate are formed when alcohols react with concentrated sulfuric acid at about 0 degrees centigrade. The general equation, here we have an alcohol which is going to react with the alkyl sulfate. For the first reaction, where this hydrogen is replaced by the alkyl group, and then this gives an ether molecule and an alkyl hydrogen sulfate molecule. The second general equation, it is when two alcohols react among themselves to give ether molecule and water. It means that if the two alcohols are reacting in acidic medium, we'll have also substitution reaction where hydrogen will be replaced by one alkyl group from one of the alcohols and water molecule is produced. We can call this one like a condensation reaction. Let us have examples. Here we have an alcohol which is going to react with the methyl sulfate to give ether and the methyl hydrogen sulfate. I think this example is clear. We can also have this alcohol which is going to react with the methanol. The two alcohols are going to react to give an ether molecule and water. I think also the examples are very clear. Let us have the mechanism. The first step is the protonation of an alcohol. The strong acid donates electron to the alcohol by forming an oxonium ion and hydrogen sulfate ion. Second step is nucleophilic attack of methanol to the electron deficient carbon. Methanol, which is going to act as a nucleophile, donates electrons to the electron deficient carbon of oxonium ion and thus repair the electrons of the bond between oxygen and the carbon, which will result in the formation of a good living group, which is water, and another oxonium ion. The third step is the protonation of oxonium ion by the base to produce ether and an acid. Hydrogen sulfate ion acts as a base and they protonate the oxonium ion with breaking the bond between hydrogen and oxygen and neutralizing the charge on oxygen, thus forming an ether and sulfuric acid. And this is to show that sulfuric acid in this reaction was a catalyst. Here comes the reaction of an alcohol with an acid. Alcohols react with organic acids, weak acids, in the presence of mineral acids like sulfuric acid as catalyst, with the elimination of water under 100 degrees centigrade temperature to produce an ester and give off a perfume smell. This is the smell of esters. This reaction is called esterification because it consists of production of esters. Here we have a general equation. This is a carboxylic acid and this is an alcohol which react under these conditions to give, this is an ester and this is water molecule. The mechanism has shown that alcohol gives hydrogen while carboxylic acid gives OH to give water molecule. You could be thinking that because carboxylic acid is acid, it is going to give proton. It's not the case. With the research, they have found that the oxygen which was found in water was from carboxylic acid, not alcohols. So I give you the task as a homework. Find the detailed mechanism of this reaction, and in the next lesson I will ask you to demonstrate it. Here we have examples. Propanoic acid reacting with ethanol under sulfuric acid and 100 degrees centigrade temperature, they have given ethyl propanoate ester and water molecule with a pleasant smell, the characteristic smell of esters. Here comes part 2. This consists of reactions involving the cleavage of carbon-oxygen bond. The first reaction is action of thionyl halides on alcohols. In the presence of weak base-like pyridine, alcohols react with thionyl chlorides or bromides to form alkyl halides respectively. Here we have a general equation and an example. Here this is an alcohol, this is thionyl chlorides, which are reacting through substitution reaction to give an alkyl halide, sulfur dioxide, and hydrogen chloride. This is an example of alcohol which react again to give this alkyl halide. This reaction generates a gas which is an air pollutant by making acid rain. I can say this is not a good method of preparation of alkyl halides, as long as it is producing sulfur dioxide, a very dangerous pollutant in the air. So to prepare alkyl halides, it's better to use other means because this one is having serious side effects. Also, we can prepare alkyl halides from alcohols using different reagents from thionyl chloride. For example, you can use phosphorus halides, phosphorus bromide, phosphorus chloride, and the reaction will be similar. The only difference will be inside the products. The next reaction is the elimination of water molecule from alcohols. Alcohols are dehydrated by heating them with the concentrated sulfuric acid or phosphoric acid to produce alkenes. The ease of dehydration is in the order. Tertiary alcohols are more easily dehydrated than secondary than primary. Here we have a general equation where this is an alcohol, and under concentrated sulfuric acid and hot conditions, it produces an alkene and the water molecule. As you can see, during this reaction, OH from alpha carbon is eliminated together with the hydrogen from one of the beta carbons to produce water molecule. But pay attention with where you are going to take hydrogen from. According to Zaitsev, hydrogen is taken from the poor carbon to mean carbon which has fewer hydrogen atoms. For this beta carbon, it has 2 hydrogens, while this beta carbon has 3 hydrogens. So the hydrogen must be taken from here, and the alkene produced must be this with the double bond in the middle. And the reason behind, the Zaitsev's rule is explained by the stability of alkenes. The internal alkenes are more stable than the terminal alkenes. Here we have an example. 2-butanol, which is heated with concentrated sulfuric acid to give 2-butene and water molecule. For the mechanism, please visit the preparation of alkenes. You will find everything there. The third reaction is the action of halogen acids on alcohols. Alcohols react with the halogen acid to give alkyl halides. Reaction happens in a weakly acidified medium, and you heat the mixture. Here we have a general equation. This is an alcohol reacting with hydrogen halide or halogen acid to give an alkyl halide and the water molecule. When you look at this reaction, it is a substitution reaction. Let us have an example. Ethanol reacting with hydrogen bromide in a weakly acidified medium and the hot conditions will give bromoethane and water. As you can see, OH of alcohol has been replaced by bromide to form bromoethane, while H and OH combine to form water molecule. For the mechanism also, you can look at the preparation of alkyl halides. You will find everything there. We have another example where this alcohol reacts with hydrogen chloride, and the conditions here we use zinc chloride, which is a Lewis acid, under hot conditions to give again the alkyl halide and water. It is also a substitution reaction, but here we have changed the acid we are using is zinc chloride. Because hydrogen chloride is not very reactive, that's why it needs a strong catalyst like zinc chloride so that the reaction can take place. Otherwise, it will be very slow reaction. Note, the order of reactivity of halogen acid is hydrogen iodide is more reactive than hydrogen bromide, more reactive than hydrogen chloride. And the least reactive hydrogen chloride requires the presence of anhydrous zinc chloride as a catalyst. That's why you saw it in a previous example that hydrogen chloride to react, you need to use a strong catalyst like anhydrous zinc chloride. This reaction is called the Lucas test, and it is used to distinguish between simple primary, secondary, or tertiary alcohols. In this reaction, the alcohol is shaken with solution of zinc chloride in concentrated hydrochloric acid as reagents, and here are observations. Immediate cloudiness indicates presence of tertiary alcohol, meaning that because tertiary alcohols are very reactive, they immediately react. If the solution becomes cloudy within 5 minutes, then the alcohol is a secondary one. Because the order of reactivity, tertiary alcohols more reactive, secondary alcohols are the ones to follow. But primary alcohols would show no cloudiness at room temperature since the reaction is very slow. The least reactive are primary alcohols, that's why they don't show an observable change at room temperature. This picture summarizes the Lucas test and observations. From the beginning, all alcohol solutions show a colorless observation, no color in the test tubes. But after reaction has taken place, you can see observable changes which are different. From the right side, this is immediate cloudiness for tertiary alcohol, cloudiness after 5 minutes. For secondary alcohol, no cloudiness at all for primary alcohol, which means that the solution remains colorless. Now you can wonder, where is this cloudiness from? The cloudiness is due to the lack of solubility of produced alkyl halide. The chloroalkane produced is not very soluble in aqueous solution, is not very soluble in alcohol. That's why it makes suspensions in the solutions and you observe the cloudiness. And because there is no reaction in the primary alcohol, that's why there is no cloudiness in the test tube. Next time we talk about part 3, which is the reactions involving the carbon carrying OH, and these reactions are oxidation reactions. Thank you.